All right, next I want to talk about another instrument or observatory and some of the science that comes out of it. And this is the Stratospheric Observatory for Infrared Astronomy, or SOFIA. And this is a collaboration between NASA and a German space agency, DLR. And what it is, it's basically a 747, so one of the largest passenger planes out there, where they've installed a 2.5 meter telescope. And so this is basically something that's, that has a mirror that's roughly the same size as the Hubble Space Telescope's mirror. And they fly it up into the stratosphere, and hence the name stratospheric. Anywhere from 39 to 45,000 feet. And the reason why they do that is the telescope is meant to observe in the mid and far infrared. So basically looking at wavelengths that are normally blocked by the Earth's atmosphere, and specifically by water vapor and the Earth's atmosphere. It turns out that water vapor is opaque at these wavelengths, and so if you can get above 99.9% of the water vapor, which this aircraft does, then you can observe these targets in the mid and far infrared. And so here is a picture of what the cabin along with the telescope looks like, and there are instruments that get mounted off the far side, and the telescope is balanced on this gimbal along with gyroscopes and shock absorbers. And the gyroscope is used to keep the telescope pointing the right way. And then the shock absorbers are basically there to keep the telescope stable against the vibrations that occur when you are in an aircraft flying. And so you can imagine if you are flying in a big 747, there's a lot of vibrations. And I haven't been able to find the video, but I have a friend who works on SOFIA, and he's told me that he's been on board, and when you're on board looking at the telescope, it looks like the telescope is a blur. It appears as if it's shaking at a high rate, but actually what's happening is that you on the plane are vibrating, but the telescope is staying completely mobile and stationary. So that's how good the shock absorbers are to keep it completely stationary so that it can observe celestial objects without any blurring effects. So here's a picture of the mirror, and here is a picture of what the left side of that telescope complex looks like. So this is the side where we can attach on instruments. And then the instrument that this paper uses is a German instrument called, well, the GREAT part stands for German Receiver for Astronomy at Terahertz Frequencies, and is basically an upgrade to that allows them to do even better observations than the original instrument. And so the paper that came out just in the last few weeks has to do with the Orion molecular cloud. This is in the Orion Nebula, and so this is a combination of the images that were taken by the upGREAT instrument. And to understand what we're seeing, what I have to do is we're going to have to go and look at the Orion constellation, and this is not something that you would see when you go outside, let's say tonight, and look at Orion, because you'd have to have eyes that are probably 10,000 times larger than what you currently have in order to see all the faint features. But we can turn on some constellation lines. And so here are the three belt stars. This is the sword of Orion, which contains this normally very faint nebulosity. But the Orion Nebula is a star-forming region right in the middle of that sword. The Horsehead Nebula is right about there. And all this reddish glow is from hydrogen emission, hydrogen gas that's been excited by starlight in this region. And if we look at the Orion Nebula with the Hubble Space Telescope, you see all this amazing emission. What is happening is that there are thousands of stars being born from the molecular gas in this region, but there's one very massive star in the center called Theta 1c Orionis that is lighting up this nebula. It pumps out a huge amount of ultraviolet photons, and it scours the winds and the UV photons from not only Theta 1c, but the other stars in this region, has basically excavated out a cavity in the molecular cloud. And all this glowing emission is the UV radiation exciting the gas at the edges of the molecular cloud. Here is a picture in Spitzer, and it looks very different, although you still see this rough cavity. So this cavity that you sort of see in visible light in the infrared shows up like this. And what happens when you go into the infrared is you can peer through a lot of the gas and the dust. Infrared light the gas is much more transparent to the infrared light. And then oftentimes what you're seeing is actually emission, the infrared glow from the dust itself that's located in this molecular cloud. But here we're seeing much more easily the many thousands of stars, and here in the center, the density of stars increases quite a bit. But all these stars are relatively young that have been born in the Orion Nebula in the last million years or so. Here are three other images. Here's another Spitzer image of the Orion Nebula. So the nebula again is down here. This is from the Herschel Space Telescope. So this is yet another infrared wavelength, but this again traces the dust emission. So the warm dust will emit in the infrared wavelengths. And here we're far enough in the infrared that no stars appear. So you're only seeing emission from the dust. And here is the SOFIA data, or one part of the SOFIA data. So again, the massive star that's blown out the bubble is located in the center here, and then you can even see the trace of the bubble that it's blown out. And so basically what is happening is that when you have this massive star, not only is it pumping out lots of UV photons, but it also has a wind that pushes outwards. And so this fast stellar wind is pushed out this bubble, and the shock of this wind slamming into the molecular gas around the star heats up the gas to over 2 million degrees. And so basically you have X-ray emitting plasma in this giant yellow bubble. And this bubble is about 13 light years across. So this is a giant structure in the molecular cloud. And with this extremely hot 2 million degree bubble, we know that hot gases like to expand. And so there's other observations that show this bubble expanding out. So it's expanding at about 13 kilometers per second. And this bubble is transparent to the super high energy UV photons. And so they stream through the plasma, and they can heat up the gas at the edge of the bubble, and that can ionize the carbon. And so instead of just neutral carbon, we have carbon plus, and this carbon plus is in this region is heated up to about 200 degrees, and that also radiates. And it turns out that the upGREAT instrument on SOFIA is perfectly tuned to one of the emission lines coming from this carbon plus ion. And so that's what this 1.9 terahertz line is. And so what the result basically is from this paper is that the amount of energy that's been deposited just from this wind is actually a pretty significant part of the energy that has come out from the star. And so you can imagine the kinetic energy of this bubble pushing outwards and pushing into the gas, and basically snow plowing, just like we've seen on the Denver streets this week of snow plows pushing snow and using the kinetic energy of the plow to push all the snow aside. Well, this expanding bubble that's been pushed out by the stellar wind and by the heating has pushed out the gas that we see in this bubble out here. So they're able to measure the energy of that gas and show that it actually dominates quite a bit over a lot of the other energy sources from that star.